My plan for this video and the next couple videos is to simply work through several examples of related rates type of problems. And so this is a classic one. But before we talk about the specifics of this, I want to again brush through the procedure that we're going to be following. So first, determine what you're asked to find. If you don't know what you're looking for, there's a really good chance that you won't find it. And so it's important that when you read the problem, that you determine what you're asked to find and make sure that you write it down. If you write down what you're looking for, there's a much better chance that you're actually going to be able to find it. Also, it's a good idea at that time to write out all the given information. Notice when you write down what it is you're looking for, suppose when you solve this, you find one piece of information, which is correct, but it's not what you're looking for. If you have already written down what you're looking for, suppose you're looking for dr/dt in some problem. Well, if you find x, that may be wonderfully correct, but you're not finished until you find what you've been asked to find. And so make sure that you write that down and also write out all the given information. So all the information is written out in mathematical language ready to be used. Make sure that you do the differential count. Notice that the differential count comes before you actually compute the derivatives. So you count how many differentials there will be before you do the actual computation of the derivatives. If there are too many differentials in the problem, then you may need to eliminate a variable if needed. And so if the differential count is too high, suppose you have 4 variables, if you're looking for one of the differentials and you're given 2 more of the differentials, but one differential is not involved in the problem in any way, then you need to get rid of that variable before you actually compute the derivative. So make sure you do differential count and make sure that count is correct before you actually compute the derivative. Differentiate implicitly with respect to time. Remember, all these derivatives, rate of change, rate means with respect to time. And then after you've differentiated, after you find the derivative, that's when you substitute the given information in and solve. Notice that what's going to happen sometimes is a variable value will be missing. If a variable value is missing, then you need to go back to the information you had before the derivative to be able to find what it is you're looking for. We'll see what that happens. Now, in the example we did earlier, that didn't occur. It actually is going to occur in this problem, so you'll see that process in action. So what I'm going to do is go through several examples over the course of the next 3 or 4 videos and work through several different varieties of related rate type problems that you'll see. There are certain kinds of problems that simply, well, they're just classics. There's the ladder problem, there's the kite problem, this is the sand falling onto a cone-shaped pile problem. There are some classic problems, and once you understand how these basic problems work, the principles that you develop can be taken forward into any scenario. So, our problem here is this. Sand is falling onto a cone-shaped pile at the rate of 10 cubic feet per minute. So we're at a quarry somewhere, and when we drop sand onto a pile, that sand will conform roughly to the shape of a cone. Now, the steepness of the cone depends upon the coarseness of the material being dropped on. If you drop gravel, it will, the size of the cone, the steepness of the sides will be different than if you're dropping very fine sand. That will be different than if you're dropping very coarse gravel. Roughly speaking, the more coarse the material, the easier it is to stack. And so for a very coarse material, the height of the cone will be relatively larger than the radius at the base of the cone. For a very smooth type of material, the material will slide down the sides more readily, and the height will be relatively shorter than the height of a much more coarse material. And so the specifics of the cone depend upon the grade of material being dropped. What we have is this: sand is falling onto a cone-shaped pile, and we're given the rate of 10 cubic feet per minute. Now, here's the relationship. The height of the cone, now when we have a cone, the height is this vertical distance. That's the height of the cone, the perpendicular vertical distance, and then the radius is the radius at the base of the cone. And so it says the height of the cone is always 6 times the radius at the base. How fast, here's our question, how fast is the radius increasing when the when the height is 12 feet and we're given the volume of a cone formula? So, sand is falling onto a cone-shaped pile at the rate of 10 cubic feet per minute. The height of the cone is always 6 times the radius at the base of the cone. How fast is the radius increasing when the height is 12 feet? As sand falls on, the height increases, the radius increases. And so the rate is falling on at a constant rate of 10 cubic feet per minute. So, what are we asked to find? What are we asked to find? So read the problem, if you need to. Remember, there is never a penalty. There is never, ever a penalty for reading the problem again. Sometimes students don't want to read the problem the first time. I actually had a student several years ago. This actually occurred. A student came into my office and asked me, could you help me with, I don't know what it was. Could you help me with problem 17? I said, fine, what's it about? And he said, I don't know, I haven't looked at it yet. If you have not read the problem, there's a really good chance that you won't know what the problem is about. So, sand is falling onto a cone-shaped pile at the rate of 10 cubic feet per minute. The height of the cone is always 6 times the radius at the base of the cone. How fast is the radius increasing when the height is 12 feet? We're given the volume of a cone. Determine what you're asked to find. Usually, not always, but usually somewhere in here, there's a question. That's a good place to look to determine what you're asked to find. How fast is the radius increasing? How fast is the radius increasing? Notice, this is extremely important. This is one of the most common errors. Don't do this. Students read this and they say, what are you asked to find? What they will say is you're asked to find the radius. Wrong, 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 wrong. We are not, it doesn't say what is the radius. It says how fast is the radius increasing. How fast is it changing? We're asked to find the rate of change of the radius. Not always, but very, very often. It's almost every time. For the work that we're going to be doing, what you're going to be asked to find is a differential, d something dt. So we're asked to find how fast is the radius increasing. We're asked to find, and go ahead and write it out, find dr dt. And that's what we're looking for. We're not done until we find that number. That's the number we're looking for. You might get some wonderful intermediate results, and they might be wonderfully correct. But you're not done until you find what you're looking for. Now, one thing I like to do, I think this is a good idea. One thing I like to do is put the units in now. What are the units we're using here? Well, notice this is cubic feet. We're in feet. The radius, height is 12 feet. So the linear distance we're talking about, radius is measured in a line. Radius is measured, the radius is going to be so many feet. So it's going to be in feet per. Now, what unit of time are we working with? Somewhere in the problem, there is a unit of time given. And it is right here, 10 cubic feet per minute, right? So somewhere in the problem, the unit of time needs to be given. And so we are in feet per minute. And so we can go ahead and write the unit in before we start. that will make the physics people happy. When you go to your physics course, they'll be glad you did that. All right, so now that's what we're asked to find. Also, what are we given? Sand is falling onto a cone-shaped pile at the rate. As soon as you see rate, or how fast something is happening, or how slow something is happening, the rate, that's a differential. This is the rate of 10 cubic feet. And so we're given 10, this is the given information, 10, and we're given feet cubed per minute. Now one thing that will help you know this is if it's given as a quantity, in this case, is cubic feet per minute, this tells you before you even start, you know what this denominator, this is a denominator expression. You know this is in dt, because this is per minute just like this is per minute. It's a rate of change. But what quantity is this talking about? Feet is a measure of linear distance. Square feet is a measure of area distance, two-dimensional. Cubic feet, this is a third-dimensional measurement. It's right here. And what is measured in 3 dimensions? Volume. So we're given dV dt because volume is 3 dimensions. So just paying very close attention to what is actually given, and the notation actually guides you through to what must be correct. We're given the rate of change of the volume. You know this is volume because this is cubic. Later on, we'll do a problem where the area is changing, and you're given the rate of change of area. That will be in square. It might be in square meters. It might be in square inches. It might be in square feet. It might be in square miles. But we're talking about area that would be in square units. If we're asked, if you were given that the height is changing at the rate of, if you're given height changing, that would simply be in feet, not square feet, not cubic feet, just feet. Because feet or meters or miles or inches or centimeters, those are linear measurements. Square would be area measurements, and cube would be volume measurements. So be very careful when you read. That will help you know what it is you're being given. Excuse me, what else are we given here? The height of the cone is always 6 times the radius. This is read it and write it from your glory days in basic algebra. Height is height. Remember verbs. Verbs mean equals. The height is, verbs mean equals, 6. 6 means 6. Times means times. The radius means the radius. Height is 6 times the radius. Height is 6 times the radius. It's read it and write it. And then the last piece of information is how fast is the radius increasing? That's what we're looking for when the height is 12 feet. So we're given h is equal to 12. And we're also given this, I'm going to erase my picture here. We're also given that volume is 1/3 pi r squared h. Now, do you remember this bit? Do not put 12 into here at the start. Do not. Substitute given information is the last thing that happens. We got a lot of stuff to go before then. If you put 12 into here and work this problem, what you get is garbage. Actually, what you get is a bunch of zeros. It turns out that the problem becomes a static problem, and nothing's changing. And so if nothing's changing, the rate of change is always going to be 0. So substitute is the last thing that happens. First thing we have to do, okay, we got everything written down. Next thing is differential count. If we take the derivative here, remember pi is not a variable. We have 1, 2, 3 variables. dv dt, do we want dv dt in the problem? Do we want dv dt in the problem? By that I mean, are we looking for dv dt, or are we given dv dt, or neither one of those? Well, dv dt, yes, we do want that one in the problem, so yes, volume passes the muster. How about dr dt? Do we want dr dt in the problem? Yes, that's the one we're looking for. We stinking better have dr dt in the problem. What about dh dt? H is here, but not dh dt. We do not have dh dt in the problem, and so we need to eliminate a variable. You must eliminate the variable before you differentiate, before you do the derivative. Well, if you do the derivative here, then we have dh dt in the problem, and there's no way to get rid of it. And so, differential count is important before the derivative. Yes, dv dt, yes, we do want that. dr dt, yes, we do want that. dh dt, no, we do not want that. And here's what that means. We need to eliminate the variable. There must be something somewhere in the problem given which allows you to get rid of h. If that's not given, the problem cannot be done, not just by you, but by anybody. All right? So somewhere in here, there needs to be some piece of information that allows us to translate height into one of the other variables. And it is right here. We may take h out of the problem. In its place, substitute 6r. Notice we're not substituting in the constant values. It is a variable value. This is the reason this had to be given was because we need to eliminate this variable. If this piece of information or something like it is not given, this problem cannot be done, the end. And so we must eliminate h because we do not want dh dt in the problem, and this piece does it. So in place of h, place 6 times r. And so this implies volume is 1/3 pi r squared times 6r. Now simplify. V is equal to 6 times 1/3 is 2. 2 pi, this becomes r cubed. Notice dimensionally this is correct now. And dv dt, yes. dr dt, yes. Differential count is now correct. Now we differentiate implicitly. Now we find the derivative. The derivative of v is the derivative of v. This is now just the power rule. Power rule. All right? So the derivative here is 3 times 2 pi is 6 pi r squared dr dt. Differential count, check. Differentiate implicitly, check. Substitute given info and solve. So substitute into here all the given information. dv dt is 10. 6 times pi. What is r? R is, notice, we don't have a value for r given. We do not have a value for r. If a variable is missing, go back to before the derivative. Go back to before the derivative and find it. We need a value for r, and we're given h is equal to 6 times r. And what else are we given? We're given height. We're given height. Height is 12. So somewhere out of here, we need to be able to find what is r squared. We do know dr dt. That's what we're looking for. dr dt is what we're looking for. All right. So our last piece is we need to find the value for r. Well, we know, again, if a missing variable value is missing, we have to go to the information before the derivative, which is here. All right. So if we know h is equal to 12, now we can substitute 12 into this equation. Notice how we're substituting values after we've done the derivative. So from these two equations, we can say 12 is equal to 6r. I'm going to run out of space here. 12 is equal to 6r, which is to say, divide both sides by 6. R is equal to 2. And so I need my value for r squared. I need a value to plug right into here. R squared, I'll put my squared on the inside. What is r? R is 2. So this is my 2 squared. So here we go. dv dt is 10 because that was given. 6 is what we inherit from the derivative. Pi we inherit from the problem. Constant multipliers multiply along. R, we're able to find r because of our given information here. H is 12. We back solved to find r. And so we found r is equal to 2. So now we have r squared is 2 squared. dr dt is what we're looking for. And so I'm going to erase a little bit of this just so I have some space to write. I'm going to copy what I've written down here. I'm just going to recopy this. I have 10 is equal to 6 pi. I have 2 squared and dr dt. And solve for dr dt. That's what we're looking for. So what do we have? This implies 10 is equal to, that's 4. 6 times 4, that's 24 pi dr dt. Divide both sides by 24 pi. And so we're left with dr dt is equal to 10 over 24 pi, which you may certainly leave. That is more than sufficient. If you wish, you may reduce that fraction. That would be 10, or that would be 5 over 12. Does that look right? 5 over 12 pi. That would be sufficient. Excuse me. And so that is our value for dr dt. That's what we're looking for, dr dt. I'm going to write this as 5 over 12 pi. And that's our value for dr dt. Now, this doesn't take nearly so long if you don't explain it as you go. And so, the process, I've erased one piece of it. Determine what you're asked to find, write it down, write out all the given information. Do the differential count, eliminate a variable if needed. Differentiate implicitly, and then once you've differentiated implicitly, that's when you substitute the values to be able to find the piece that's missing that you need. All right, so what's next to do is I'm going to go through several examples. In fact, I'll go through another example of the cone-shaped pile problem, just so we have another to go through for the practice. And hopefully, now that we've talked through it once, the actual computation won't be taking quite so long. Again, this doesn't take nearly so long if you don't need to explain it as you go. So we'll do another problem here with a cone of sand or something falling onto a cone-shaped pile, and we'll see if we can work that out.